Steal energy from a black hole, and you could power human civilization for 1 billion years. Physicists say it's not science fiction. It's already written into the laws of physics. And the strangest part? A black hole doesn't just destroy energy. It can hand it back to you, bigger than you gave it. Here's the thing nobody tells you about black holes. They're not just cosmic vacuum cleaners, they're spinning. And when something that massive spins, it doesn't just sit there, it drags the fabric of space and time around with it, like a whirlpool dragging water. This isn't a metaphor. This is a real, measurable effect called frame dragging, and it was predicted over a century ago by Einstein's equations, confirmed by satellites orbiting Earth itself. Now scale that up to a black hole. Around every spinning black hole, there's a region called the ergosphere. It sits just outside the event horizon, the point of no return. Inside the ergosphere, space itself is being dragged around the black hole so violently that nothing, not even light, can stand still. You are forced to move with the rotation, whether you like it or not. But here's the twist. Unlike the event horizon, you can still escape the ergosphere. You can go in, and you can come back out. And that one fact changes everything. In 1969, a mathematical physicist named Roger Penrose, yes, the same Penrose who later won the Nobel Prize in 2020 for proving black holes are a real, unavoidable consequence of Einstein's relativity, worked out something extraordinary. He showed that if you threw an object into the ergosphere and split it into two pieces, one piece could fall into the black hole while the other piece escaped back out carrying more energy than the original object had. More energy from nothing. That sounds like it breaks physics. It doesn't. The extra energy is stolen, quite literally, from the black hole's rotation. Every time this happens, the black hole spins a tiny bit slower. You are not creating energy from nothing. You are draining a cosmic flywheel that has been spinning, in some cases, since billions of years after the Big Bang. This is called the Penrose process, and it's not a fringe theory. It's standard, peer-reviewed physics taught in general relativity courses at universities around the world. The only debate is not whether it works, it's whether we could ever build the technology to use it. Here's where the numbers get almost impossible to comprehend. A supermassive black hole like the one at the center of our galaxy, Sagittarius A, has a mass of about 4 million times that of our Sun. Rotating black holes can carry up to roughly 29% of their total mass energy in spin energy, extractable in principle through mechanisms like the Penrose process. 29% of 4 million solar masses converted into usable energy is a number so large it stops meaning anything to the human brain. For comparison, the Sun itself only converts about 0.7% of its mass into energy through nuclear fusion, and that single reaction powers our entire solar system. A spinning black hole is, in theory, a far more efficient energy source than any star. But Penrose's process is not the only way scientists have proposed to steal power from a black hole. In 1977, astrophysicists Roger Blandford and Roman Znaczek proposed a different and arguably more realistic mechanism, one that many scientists now believe is actually happening in real galaxies today. It's called the Blandford-Znaczek process, and it doesn't involve throwing objects into space at all. Instead, it uses magnetic fields. Here's how it works. Supermassive black holes are almost never alone. They're usually surrounded by an accretion disk, a swirling ring of superheated gas and plasma, ripped apart from stars and clouds that wandered too close. This disk carries powerful magnetic field lines. When those magnetic field lines get anchored near a spinning black hole and twisted by the drag of the ergosphere, they act like a gigantic cosmic generator. The rotational energy of the black hole gets funneled along the magnetic field lines and blasted outward as jets of particles moving at close to the speed of light. These are not hypothetical. Astronomers have actually seen them. The jets shooting out of the black hole in the galaxy M87 stretch for over 5,000 light-years, and the Event Horizon Telescope captured the first-ever image of this exact black hole in 2019, followed by images of its magnetic field structure in 2021. In 2023, Further polarization data strengthened the case that the Blandford-Znajek mechanism is genuinely powering that jet. This isn't speculation anymore. We are watching a black hole convert its own spin into raw, visible energy, broadcasting it across thousands of light-years of space. So why aren't we building black hole power plants right now? Because the obstacles aren't scientific, they're almost absurdly practical. The nearest known black holes to Earth are still thousands of light-years away. Even at the speed of light, a signal, let alone a spacecraft, would take thousands of years to arrive. And building anything close enough to a black hole to harvest its spin means surviving tidal forces that can stretch matter apart atom by atom, radiation levels that would shred unshielded electronics in seconds, and gravitational environments so extreme that our current materials science has no answer for them. There's also the matter of scale mismatch. Human civilization currently uses somewhere around 600 exajoules of energy a year, according to recent global energy data. A stellar mass black hole's rotational energy reserve is so large that even a tiny fraction of it, extracted safely, would dwarf our entire planet's energy needs for millennia. We're not talking about upgrading power grids. We're talking about a source of energy so disproportionate to our current needs that it almost breaks the concept of an energy crisis entirely. This is why some physicists and futurists frame black hole energy extraction using something called the Kardashev scale, a way of measuring how advanced a civilization is, not by their technology, but by how much energy they can control. A Type 1 civilization harnesses all the energy available on its home planet. A Type 2 civilization can harness the entire energy output of its star. A Type 3 civilization operates on the scale of its entire galaxy. Right now, by most estimates, humanity sits at less than a Type 1. Mastering black hole energy extraction, even partially, would be a signature of a civilization crossing firmly into Type 2 territory and beyond. That's the real reason this topic isn't just cosmic trivia. It's a benchmark for where our species could theoretically end up, if we survive long enough and advance far enough to reach it. There's another twist that makes this even stranger. Stephen Hawking showed in the 1970s that black holes aren't eternal. They slowly lose mass over unimaginable timescales through a process called Hawking radiation, a quantum effect where black holes very gradually radiate energy away and shrink. For a supermassive black hole, that process would take far longer than the current age of the universe to matter. But it's a reminder that even black holes, the most extreme objects physics has ever described, are not truly permanent. They too are running down a clock, just one measured in numbers that make the age of the universe look small. So here's where it leaves us. We have two real, mathematically sound mechanisms, the Penrose process and the Blandford-Znajek process, that show, without any fictional shortcuts, that spinning black holes are sitting on almost incomprehensible reserves of extractable energy. We have direct observational evidence from the Event Horizon Telescope's images of M87 that one of these mechanisms is very likely already happening in real galaxies. And we have a civilization on Earth that currently can't even build a spacecraft that could survive the trip to attempt it. The physics says it's possible. The engineering says we're nowhere close. And the timeline says this might be a project not for us, but for whatever version of humanity, or whatever descendant of humanity, exists tens of thousands of years from now. If a civilization thousands of years more advanced than us figured out how to tap a black hole's spin, do you think they'd share that power or hide it? Drop your answer in the comments and follow for part 2, where we break down how close we actually are to detecting alien civilizations doing exactly this.